There we go. Joseph, Joey, it's over to you.
Great. All right, so I'll get my screen shared and we should be good to go. All right, so first off, thanks very much to Adil and the rest of the organizers for this wonderful opportunity to share my work with a very broad audience. And I will not assume that you're all Sheets people, so I'll sort of start with some things to get folks up to speed who don't work with Sheets every day. And I guess the first thing I want to point out is the two pictures you're looking at here. So on the left, you're looking at the inflatable barrier that's keeping water in this inflatable pool for children. A photo taken in my backyard a couple summers ago. And on the right, you see a photo from my lab, which is an extremely thin polymer film, just about 50 nanometers thick, but it's about 3 millimeters wide in its lateral dimension. And the thing that I hope is striking you is that there's this kind of fascinating buckling pattern that you see in the left picture and also mirrored on the right picture, where these sort of diamond-shaped kind of discrete buckling patterns are lining up in chains. And so this is the talk. This is what we're going to grapple with for the next 40 minutes, is what are these buckling patterns and what can we learn about them? So just as long as you're here, I'll just advertise my work is in sort of two branches in my lab. So this is just a snapshot of some of the other investigations that my group has done on the interplay between geometry and mechanics in thin solids. And we also look at memory behavior in amorphous materials, focusing mainly on suspensions, but also looking at connections across different material systems for how disordered materials can learn and remember and forget things. Okay, so that's not what this talk is about, but that's kind of a preview of what my lab is about. So I've chosen just to talk about this one particular project, and I want to highlight the folks who were involved with this work, who really did all the measurements. The first is Yusra Timune, which was my postdoc a couple of years ago, and then a collection of graduate students, Raj Day, Zach Schreckengost, and Monica Ripp, and then a summer intern, Jessica Stelzel, who did some measurements that were crucial to this project as well. And this work is reported in PRX in a paper that came out last year. We were very delighted to get a little write-up in APS Physics Magazine, so we were happy about that exposure. And then I should just point out that this is funded by a few different mechanisms through NSF. The IGERT paid for Monica, the RU paid for Jessica, and my career grant took care of the rest. Okay, so done with the business, on to the science. So this is a talk about patterns, and patterns are wonderful. Here's an old example of a pattern. This is a frieze pattern on a stove in ancient Greece. And the lovely thing about patterns is if you're missing a chunk of the material, you can kind of figure out what should have been there. Okay, so this is the missing piece in this pattern. And of course, we can do this on a small scale. We can do this on a large scale. You see a bunch of pillars here and you see, okay, pillar, 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 pillar. Well, there was probably a pillar there, but I think it fell over. So that's one thing that's lovely about patterns. In my lab, we look at wrinkle patterns. So this is a wrinkled polymer film. And once again, the thickness is in the order of 50 to 100 nanometers. The lateral scale is on the order of centimeters, or about 1 centimeter. And of course, if you excise a little chunk out, you can sort of figure out what would have been there before you cut it out. So wrinkle patterns actually have a number of different uses. Let me tell you how this experiment was set up first. So we make these polymer films on glass microscope slides or other glass substrates. We do a process called spin coating that gets an extremely uniform, extremely thin layer of polystyrene laid down on the substrate. Then you can sort of carefully dip the substrate into a water bath and the film will separate from the substrate and come off onto the liquid interface. And then once it's there, you can sort of dream up all kinds of games that you might want to play. You might want to put this in an oil phase. You might want to ball this thing up into a water droplet, apply boundary conditions, apply boundary loads, sort of, this is the playground. That you can decide how to load the sheet or frustrate the sheet in different geometries. And then we observe what happens and try to quantify everything. And this is just a photo of a student, Graham, who is sort of carefully transferring a sheet off of a substrate into a water bath. And in this case, the substrate is curved. So this is a curved shell that's being transferred to a flat water bath. And here we're looking at the geometric frustration of laying a intrinsically curved thin solid on a flat water bath. So wrinkles are lovely. There's lots of things that wrinkles tell us about nature. For one, they're ubiquitous, so you find them everywhere. You find them in this skin of this drying apple. You find them on your own skin. You can even find them on a much smaller scale, where here a single cell is crawling across a substrate and exerting forces. And this wrinkle pattern here is telling you something about the forces that the cell is exerting on the substrate. Okay, so wrinkles can maybe measure something. They can tell you about forces in a system. And so that's a nice feature. And another example here is this vesicle you're seeing. So this is a lipid bilayer, and this vesicle is a thin membrane. It's not elastic, but it's a thin membrane with a bending modulus. And when this thing is subjected to a shear flow, you get a compressive direction in the vesicle, and this causes undulations or wrinkles of the vesicle. Okay, so these wrinkles are everywhere, and I hope you're getting a picture that these things are probably useful. And this is true. Wrinkles are a non-invasive probe of forces and material properties. That is, once we build up the fundamental framework for doing so, we can look at a wrinkle pattern and we can tell something about the forces that have been exerted, or perhaps something about the elastic modulus of the material that's wrinkling, et cetera, et cetera. So this is sort of the applied bent for why wrinkles are useful. And there's a completely different reason that I think wrinkles are important, which is that they're fundamental. They're telling us something fundamental about how nature is behaving under our noses. So this is going to take a little bit longer to explain, but we have time. So I'm going to spend the next 5 or 10 minutes describing some of the recent kind of fascinating fundamental things about wrinkles. And kind of the main thing that this stems from is a separation of energy scales. So for any material, if you make it much thinner than it is wide in its lateral dimension, you'll get the separation of energy scales, where the material will become very easy to bend in relation to how hard it is to stretch the material. And one very important fundamental result of this is that sheets like to form isometries. That is, if I take this sheet of paper and I put it under some kind of different boundary conditions with my hands, the sheet chooses deformations such that distances along the sheet are preserved. Okay, so and the reason for that is that these isometries avoid the expensive stretching energies, and they pay only the cheap bending energies for this to happen. Okay, and so really, I think I want to take even a step back further than that. So let's step really far back. Let's step all the way back to Galileo. And this is a lovely etching that was made when Galileo was sort of grappling with this question of if I take a cantilevered beam and I anchor it on a wall, and then I hang a mass off of one end of this beam, what should be the equilibrium shape of deformation of this beam? And this is a tough question, at least at this time. Galileo did not solve it. it would take quite a while for James Bernoulli to come along and to think about the problem again. And in fact, James Bernoulli did not solve it, but his nephew, along with Euler, they made some pretty important progress. Okay, so this is sort of a very sort of flimsy reed or rod that you're looking at, and it has a mass hanging from it. And again, the question is, what is the shape? What is the deformation that this rod makes when it's subjected to some boundary conditions? And what Bernoulli did was to point out, okay, so let's characterize this equilibrium shape by its curvature at every point along the shape. So the curvature here is 1 over the radius of curvature locally at each point. And then let's integrate the square of those curvatures along the object. And that's going to be my system energy. That is, the bending energy is the energy that I need to know, and the bending energy is the integral of the curvature squared along the object. And so this energy functional you're looking at is called the Euler-Bernoulli energy functional, named for Daniel Bernoulli, James's nephew. And the important thing is, one of the important things is that you don't see stretching in this. So stretching energies, these very costly stretching energies, have been taken into account as a constraint. We're not going to allow this rod to stretch or compress. We're keeping its arc length fixed. And then with that constraint, we're trying to minimize the bending energy via this curvature. Okay, so that's 1D. Now let's fast forward and go into 2 dimensions. So from rods to sheets. And just to point out another kind of famous person along the way, this is Max Born's PhD thesis. Max Born of quantum mechanics fame actually wrote his PhD on the Euler elastica. So there are really a lot of great minds that contributed to this problem along the way. Okay, so from rods to sheets. So what are the isometries of sheets? Well, they're the birthday shapes, it turns out. So rolls of wrapping paper make cylinders. So cylinders are isometries of this sheet. And well, they're cones, like a birthday hat. This is a nice isometry of a sheet. And if you want to be really unique and bring a kind of a strange gift to a birthday party, you might consider bringing a tangent developable to a birthday party. This is the third a full classification scheme. This is the third and final type of deformation of a sheet that avoids stretching. So you might ask, is this it? Is this all you can get, or can we get more than this? And the answer is you can get some more shapes if you allow a little bit of stretching. So let's allow lower dimensional sets of stretching. Let's allow stretching at a point, which is the example here is this what's called a D-cone or a developable cone. So this is now a vertex where stretching is concentrated. But once you get away from some little core region, everything else is isometric. And if you take 2 of these D-cones and you put them in proximity to one another, you get what's called a stretching ridge. And I can't help but point out, since Tom Witten's in the call, Lubkovsky and Witten and others are kind of famous for this ridge. So this is concentrated stretching along a line that joins these 2 points. And so this is kind of a huge fundamental insight into how paper or any other thin object behaves when you confine it. It turns out that thin materials do not like to homogeneously distribute energy when you confine them. They like to concentrate energy when you confine them. They like to concentrate it at vertices and ridges and other such lower dimensional sets. Okay, so that's one kind of, to me, very fascinating fundamental thing about sheets is this stress focusing property that they seem to have. All right, so then you might ask, okay, is this it? Are these now all the kind of low energy states that you can get for an elastic sheet? And one thing that you might notice about these surfaces is that they all have a direction on which the curvature is 0. That is, if you take some point on these surfaces and you're a little ant living on the surface, you can find some direction to look in along which the surface is identically just a straight line. And so that is, these are all so-called singly curved surfaces. And so is that all you can make? Is it impossible to make a doubly curved surface with an isometry? And one of the fascinating results that I got to be a part of in recent years is this idea of an asymptotic isometry. This is the idea that you can use wrinkling to make a doubly curved surface, but approximate, that is approximately. So I can take wrinkles and put them on a little curved polymer, a flat polymer film, and curve it into an approximately spherical shape. Or I can take wrinkles and put them on an initially flat film and make them into a hyperbolic shape, like you're seeing on the left, where I'm indenting a sheet. And the trick here is that this is isometric in a limit. It's the limit where the wrinkle amplitude and wavelength goes to 0 that we're achieving a 0 stretching type of solution. So let me walk you through kind of the idea of how this works. I mean, you're seeing it in these images. It really does work in the lab, but this is conceptually what's happening, is that in the plane, these wrinkles are allowing you to have in-plane compression without actually stretching the film or compressing the film. So I can bring material points closer together with these undulating patterns between them. And then I can take a limit where the amplitude of those wrinkles and their wavelength goes to 0 at a rate where the total amount of compression stays fixed. So if I cut the wavelength in half and if I cut the amplitude in half and the wavelength in half, I've kept the compression, the in-plane compression fixed. And then I take the limit where that wavelength goes to 0, and now I can approximate a plane that's, I can approximate a line on the plane with a shorter line on the plane. So this is now the secret to making a doubly curved surface, is you do this now in a two-dimensional sense. And so this is called a submetric space. That is, we can take distances in the plane and we can shorten them with these undulating wrinkly solutions. And if I can shorten any direction I like in the plane, then I can make a spherical cap or a saddle purely by shortening in the proper way. Okay, so that's a little vignette. That's sort of, that's most of what I wanted to tell you about thin sheets in general. And now let's jump into wrinkles and crumples in particular. So I'm going to jump past a couple of slides. So sort of second half of my talk is going to be devoted to two particular morphologies that you can see in sheets. We've talked a little bit about wrinkles, and those are sort of smooth extended deformations. And we've talked a little bit about stress focusing, and so those are sort of sharper deformations. And the question is, when should you get one or the other? That is, when do I expect a smooth solution to some confinement, and when do I expect a sharp solution to some confinement? And the answer that we have now is that there's a threshold, that depends both on curvature, the imposed curvature that you're applying to the sheet, and also on the tensile stresses that you're applying at the boundaries. And we have a pretty good characterization of this in the lab, but a theoretical understanding of this is still lacking. So that's kind of hopefully where this field is headed, is to get a deeper understanding of this. And the story starts with some lovely experiments done in the lab of Narayan and Menon by a graduate student at the time, Hunter King. And what Hunter did was he took one of these thin polystyrene films and he placed it on a water meniscus. And then by changing the volume of liquid, he could inflate or deflate this little meniscus to go from a flat shape to a curved shape where the sheet is forced to live. So on the left, you see an image where this planar film is living on a planar liquid surface and everyone's happy. On the right, you have this planar film living on the curved liquid surface, and you have sort of what I would call the paper plate isometry, where you have little wrinkles along the edge of the plate that allows it to bowl up, or in this case, bowl down very slightly. But now the really fascinating thing is that if you go to slightly larger volumes, slightly higher curvatures for this water droplet, you get a completely different solution. You start to get these sharper stress focusing objects. And so let me zoom in on these to show you what I mean. So in the top picture, these are these smooth undulating kind of sinusoidal wrinkles. And in the bottom, we see sort of sharp, discrete objects where you might almost think of these as wrinkles that have well-defined ends within the bulk of the sheet. And it's at these endpoints of these red lines I've drawn, that you perhaps would imagine stresses are being focused. And so, okay, so why is this interesting? Well, this is a symmetry breaking process, so that's kind of fascinating. We go from axial symmetric solutions to ones with increasingly broken symmetries. This stress focusing process could be important for engineering applications. If you want to avoid material degradation or material failure, you want to sort of engineer around stress focusing where you don't want it. And for me, it's just a beautiful response with very little intervention. You get these rich patterns from a very simple setup. And wine, it turns out. This is a photo of a wine storage tank that was initially a nice cylindrical tank. And there was an earthquake in this region of California, and this tank buckled. And if you look at these buckling patterns on this very large steel tank, and you compare it to this image from my lab on a much smaller scale, I think the similarity is striking. So these crumples, whatever they are, they look to be scale invariant. You can get them on any scale that you like. And so it's looking like they're really a general thing. That is, they're not specific to a material or not specific to any particular setting. You can kind of have them anywhere. Even on a little inflatable pillow of air. These are these bags you get when you order something from Amazon or anywhere else. If you hold one of these things in your hand very loosely, you get crumpled undulations around the edge. And if you just squeeze them just right, you can iron these things out into wrinkles just by modifying the internal pressure of the bag with your thumb and fingers. And this is a photo, again, on a larger architectural scale. This is a sunshade. I was on a day trip with my family in Geneva, New York, at one of the Finger Lakes. And you look at these sunshades and you see these little, diamond-shaped buckles, and it looks like the same thing all over again. And they're screaming for an understanding, for an explanation. And okay. There's example after example. This is now a SpaceX rocket that took off and then landed. And when it landed, it sort of landed with a bit too much velocity, and the top of this thing buckled. And there you have them again. So I think it's very striking that you can have you can have these things really anywhere you look for them, you can find them. But we still lack a fundamental understanding. So let me be a bit more specific about what I mean by what is lacking. So what would we hope for from a theory? Well, we'd like to know something about the transition. That is the transition from smooth wrinkles to crumples, a continuous or discontinuous transition in the language of phase transitions. We'd like to know what the order parameter is. And then once you've done the transition and you're in this crumpled state, we'd love to know the energy scaling. How does the energy of the system scale with the thickness of the sample or the Young's modulus of the sample, et cetera? What are some of the length scales that appear? That is, you see these diamond-shaped patterns, they have a length that they want to be. It's much bigger than the thickness, but it's smaller than the system size. So what is that emergent length that these buckles would like to be? And what's the asymptotic behavior if you send thickness to 0? What's the asymptotic behavior of the system in that or any other limit? So that's what I mean by a fundamental understanding is lacking. Okay, so hopefully I've convinced you that crumples are kind of everywhere. We want to get to a quantitative understanding. an important intermediate step, which we were able to make through some experiments in my lab, is to isolate these things in the simplest possible controlled setting. So here's one experiment where we started to isolate these things to tease them apart. This is an experiment by my grad student, Monica Ripp, where she took a circular polymer film and started indenting the film with a little spherical probe and pushed it into a water bath. And so I'm going to play the video for you now. At the beginning of the video, there's a slight indentation already. So you already have wrinkles at this stage. And she's just going to push a little bit further down to see how they develop. So again, we're seeing a transition from a very smooth undulating solution to a solution with slightly more of a symmetry breaking with these discrete structures appearing that we're calling crumples. And so I think this is a very important kind of observation, that you can get these things in these two experiments because the geometries, the imposed geometries are fundamentally different. Excuse me. On the left, you have a spherical geometry that the sheet is being confined to. On the right, you have a hyperbolic geometry, that is the overall gross geometry that this sheet is living on has negative Gaussian curvature in the right image and positive Gaussian curvature on the left image. And so these crumples are at least general enough to solve problems that come up both for positive Gaussian curvature and negative Gaussian curvature. So that's one kind of observation that can maybe help us understand these things a bit better. What I'd like to ask now is, are these things even unique to what I would call incompatible metrics? That is, we're seeing these things come up when I put a sheet on a Gaussian curvature surface. So maybe it's the case that this is something fundamental to mapping two metrics together that are incompatible with one another. On the other hand, could we tease apart these two effects? On the one hand, the curvature of these different interfaces is leading to compression, and compression is what causes the wrinkly solution. And then perhaps there's another threshold, which is when the curvature gets large enough, they sort of fragment into crumples. So the question I want to pose is, can you get these things without an incompatible metric? Can you get these things on a cylinder, for instance? And so that's the experiment that my postdoc Yusra set out to do, is to try to get these crumples on a cylinder where, just to remind you, the cylinder can easily be achieved without any buckling whatsoever. So it's an isometry of the plane. There's nothing incompatible about this. So first we're going to form a cylinder, and then we're going to ask what happens when I come in and compress, or when Yusra comes in and compresses that cylinder from the side. And the way she's doing this is in a little trapped little liquid meniscus that's trapped between two walls. And so these two side walls are pinning the contact line of this water meniscus. And then as she raises or lowers the amount of fluid in a reservoir to the side, she can then start with a flat meniscus and then curve it up into a cylinder or curve it back down into a plane. And so in this system, we can tune the radius of curvature of the liquid cylinder, and we can also apply compression to the film with two barriers on the side. So in this video, what Yusra is going to do first is start with a rectangular polymer film living on a planar liquid bath, and then come in and compress it. And so at this stage, we just have wrinkles living on a planar substrate. So that's all fine. And now she's going to raise the level of the water to force this liquid meniscus to curve into a cylinder and force those wrinkles to wrap around the cylinder shape. And now you get the crumples starting to form. Okay, so once again, we are compressing with the two barriers on a planar bath. Now we're holding the compression fixed and raising the water height to curve the water into a cylinder. So this was, very thrilling for us. This is, I think, a vast simplification of the problem, because now a theoretician can start to address this problem perhaps as a perturbation around a cylinder. And this is a much, I think, more tractable setting than trying to set this problem up on a sphere or a hyperbolic surface. So this offers some hope for theoretical attacks. And my collaborator, Ian Tabasco, is working hard on this currently. So, but we also saw these things in these inflated structures. And so I'd like to sort of quantify this in these other experiments as well. That is, I mean, the kiddie pool is nice, the Amazon bag is nice, but can we do this in a laboratory setting where we're really controlling what's going on with the geometry of the bag and the pressure inside, and we're measuring everything, and we can really characterize the transition on this larger inflated surface scale. So that's the question: how do I make crumples in an inflated membrane with an asterisk? The asterisk is in a well-controlled laboratory setting. And so this is where my graduate student Raj came along, and he started doing the following experiment. He took a rectangular film where we order sheets of plastic from McMaster Carr, and he takes a 2x1 rectangle and folds it over on itself, and then uses a heat sealer to seal 3 of the sides of the bag, leaving the 4th side with a nice boundary condition with no glue or sealer or anything on it. And it's that sort of that 4th side where we're going to look for the wrinkles or the crumples forming as we inflate the bag with gas. And while we're doing this, we're monitoring the pressure inside the bag as we sort of quasi-statically inflate the system. So here's a video of one of these bags sitting on a table. It's almost totally deflated with a pressure gauge on the right, and then the hose on the left and the hose on the right inserting the air. Here we're starting with the sharper crumpled solution. And then when the pressure gets large enough, it transitions to the smoother wrinkled solution. I'll play that again. Again, moving from these sharper diamond-shaped crumples into the smoother undulating wrinkles. So now we're seeing the transition finally to the wrinkled state here at high pressure. Okay, so now we're going to kind of tie this all together. That is, just kind of as a review, we've seen, well, originally crumples were discovered by King and Menon on this spherical confinement setting. And so these are Hunter's pictures from his PhD thesis, showing the 2 wrinkled and crumpled states. Then we have Monica's experiments showing that you can get this in a hyperbolic geometry. You have Usser's experiments showing that you can get it even in this simpler cylindrical setting, which I think is the ideal place to study these things now. And then finally, you have Raj's experiments showing that, well, we can also control them in a place without capillarity. That is, we can control them just with an internal pressure. And so that leads to another kind of convenient scale on which to probe the system. And so now I'm going to tie all these things together onto a single phase diagram. So we've built an empirical phase diagram of all 4 settings, where I'm showing you Hunter King's data points as these pink triangles. This dashed line is a dimensionless number that I'm going to introduce in the next slide. But for now, just take it to be some criteria for going from wrinkles to crumples. We have the experiments of Usser on the cylinder falling near the same phase boundary. The experiments of Monica falling near the same phase boundary. And finally, Raja's inflated membranes, again, falling close to the same phase boundary. Okay, so it looks like we can actually capture all of these different geometries and different boundary conditions on a single phase diagram. You notice that the axes don't have labels. Okay, that's on purpose. I haven't given you those dimensionless numbers yet, but the x-axis is telling you something about the tensile loading. So for the liquid setups, this is the strength of surface tension. So Yusra put surfactant in some of her experiments to lower the surface tension and kept her system as pure water to have a higher surface tension. So we can play with the tensile loading. In the inflated bags, this is the internal pressure. That's what you're tuning, is the tensile loading in the material. As you raise the pressure, that tensile loading is going up. On the y-axis, this is the imposed curvature. So the curvature along a wrinkle crest. That is how much are you bending that wrinkle crest around a curve setting. Okay, and so interestingly, we can even march along this phase diagram in a couple of different directions. So the inflation experiments started from crumples, and as you increase the pressure, you go to the left on this diagram, whereas all the fluid experiments were at fixed tensile loading, fixed surface tension. And here we're geometrically changing the imposed curvature going upwards from the wrinkled phase to the crumpled phase. Okay, so that's sort of how you navigate this phase diagram. Let me tell you what these dimensionless numbers are now. So briefly, there's a capillary stretching parameter that compares how much stretching surface tension is doing to how resistant is the material to stretching. So E is the Young's modulus, T is the thickness. Together they make what's called a stretching modulus. Gamma over a stretching modulus is one dimensionless number in the problem. There's another dimensionless number in the problem that tells how easily bent are your objects. All of our experiments here are in what's called the high bendability limit. So they're extremely easily bent. So that number it's important for the problem, but it's not important for the transition. It's just always high. And then we can put in another dimensionless number, which is W over R. So W is the size of the system and R is the radius of curvature that's being imposed. And so this confinement parameter combines the capillary stretching parameter, gamma over ET. It combines it with this geometric dimensionless number, the sheet size over the radius of curvature. And it's the combination of these two that creates this number that's called alpha. Okay, so where does this alpha really come from? Well, this alpha really comes from a what's called a far from threshold analysis of the Foppel-von equations for the wrinkling transition. So alpha comes out of a theoretical understanding of the wrinkling transition from the planar state to the wrinkled state. And that is well understood. What is not well understood is the transition from the wrinkled state to the crumpled state. But you can say, well, suppose it's just the same dimensionless parameter that controls it. Suppose alpha controls that one too. That would be somewhat akin to like a Reynolds number in fluid mechanics. So when Reynolds number is roughly 1, you have balance between inertial stresses and viscous stresses. And when the Reynolds number is very large, you have another transition into turbulence. So that's maybe qualitatively what the picture is here. You have when alpha is order 1, you go from a flat state to a wrinkled state. And then when alpha is sufficiently large, you go to yet another state into the crumpled state. That argument by itself is just sort of empirical. So we don't have a theory for that, but that's sort of a guess. But it does a pretty good job of describing the data. Just to say when alpha is about 150, that seems to be when you get these crumples. So that's sort of where the theory stands now. Okay, so I just have about a minute or two left, so I'm going to wrap up now. I want to just give a little bit of an impression of where we're headed with this problem into the future. So one of the things is, well, we can measure the length of a crumple, and that we've characterized experimentally, but we don't have a theory for it, and we would love to have a theory. So I can give you a data collapse for how long these crumples are versus a bunch of parameters that I use to collapse the data. I don't have time to explain it here, but this is in the paper, so you can see what the emergent length scale is. But again, these exponents are empirical. We just measured them. We don't know where they come from. The general picture that I want to get across to you is that these crumples are generic. They're generic across scales, across geometries, across materials. We have a phase boundary that tells you when to expect them, but we don't yet have a theory that sort of encapsulates all of that knowledge yet. One little sort of future-looking kind of tantalizing clue is that we've done some maps of the Gaussian curvature, the local Gaussian curvature of these buckled morphologies, and we can see stress focusing in these things. So in the middle column are these 3D scans that Jessica made, and on the right column are local Gaussian curvature maps that Zach extracted. And these bright red points and bright blue regions are where the stresses are concentrated. And we wonder whether perhaps in the limit of zero thickness, this crumpled state might turn into a kind of an origami type pattern. And so maybe crumples might be an approximate isometry of the sheet in an appropriate limit. And so that's where I'm going to leave you, because I sort of started with isometries, and I think it's fitting to kind of end the talk with isometries, but with a question mark. That is, are these crumples trying to be close to an isometry, or are they something different altogether? Okay, so is, more specifically, is there a well-defined limit where the stress focusing features shrink to zero area? That's a question. All right, so the book is always better than the movie, so I invite you to check out the details in our paper, and then I'd be happy to now open it up for questions. Thanks.